All right, check this out. Is this working? It looks like it. All right, cool. All right, hey, what's going on? My name is Tosh Dalde. I'm here with my son Ben. We're kind of in a pickle as far as not being able to do GS chemistry, and so I figured as a way to help, I'd maybe take my son through some of the textbook, and I figured, hey, if I'm going to do it, I might as well just record it and work my way through it, and then if it can be used by other students, by all means, that's cool. If not, feel free not to watch the video, I guess. My background is I'm not a chemistry teacher right now. I used to teach chemistry, and I'm a physicist, a professional physicist, but I have about 20 years of online teaching experience, and I also have taught chemistry. I've developed a whole chemistry program for different schools, and so I figured, hey, during this crazy times of coronavirus, might as well see if I can do my part to help out. And so let's just get started with the lesson. I'm gonna go straight from the textbook. I'm not gonna come up with crazy cool PowerPoints or anything. I'll just kind of talk and give my thoughts about this thing. I figured what I do is maybe recruit any other parents to see if they might want to jump in. I know that one of the parents from a student in my son's class is an actual chemist, so maybe they might want to contribute or like offer their thoughts on things I'm talking about. Hopefully everything I'm talking about is completely accurate and correct, and I'm just going to do the problem straight out of the book, but I'm going to kind of work with you through this so that way you can read the textbook and then not kind of just be confused at what you're reading, and hopefully it will make a lot of sense. So what we're going to talk about is moles. Today we're talking about chapter 7. We're going to hit this concept called moles, and I think that moles are super easy. And it all starts off with this. In fact, I'm just going to start with some example problems, I guess. So, if I were to ask you to go out to the store and buy 48 rolls of toilet paper, right? Or, okay, fine. 48 eggs. Would you, what would you do? Would you go out and count, like, open up all the things and then count 1, 2, 3, 4, 5, 6, 7, 8 and get to 48 and just be like, okay, I'm going to put it in a big shopping bag and here's my eggs?
No, I just buy 2 packs of 24.
Okay, all right. So they come pre-packaged in groups, yeah. Right? And in fact, let's not say that we get the fancy packages. Let's just say that we got the straight up like small dozen packages of eggs, 6 rows or 2 rows of 6. How many would you get?
4.
4, okay, right. So you don't need to map this out, but this is actually kind of easy, right? It's like 48 eggs. How many cartons? Well, what you would do is for a fact that 1 dozen eggs equals 12 eggs, E-G-G-S. Right? 1 dozen equals 12. And whenever we have an equal sign like this, did you guys do unit conversions yet?
No, I don't think we did.
Okay. So whenever you have an equal sign like this will set up a conversion factor that you can use. And so I can basically make this into a fraction, and I can make it into 2 kinds of fractions. It could be where you can have 12 eggs divided by 1 dozen, or you can have 1 dozen on top divided by 12 eggs. Okay, you can have 2 different kinds of fractions. You have either the eggs on top or eggs on bottom, and then vice versa. You got the dozen on bottom or the dozen on top. Does that make sense?
Yeah.
And so in this case, the problem that we're dealing with, we have 48 eggs, and so basically we're going to multiply that by some fraction. And the reason why I say it's some conversion factor is because it's not really, it's really the number 1, right? Because 1 dozen is equal to 12 eggs. That's the same thing. And so really, when you have something divided by itself, it becomes the number 1, right? Yep. So you're not changing this number at all. You're just changing the form of it. You're just changing the packaging or how we're looking at it. Does that make sense?
Yeah.
And obviously you know the answer without even thinking about it, but I mean, because like this is completely intuitive for you, right? But I could say, all right, but what we would do is, which fraction would we use? Would we use the one with eggs on top or eggs on the bottom?
The eggs on the bottom.
Why? Why the eggs on the bottom?
Because you're trying to convert them.
Exactly. And this one has the eggs on top, so if I have eggs on the bottom over here, these will cancel the units. 48 divided by 12 is equal to 4. So I know that that was super easy, and I know I'm not trying to, you know, insult your intelligence, but I'm really, here's the point, okay? What I'm trying to do is I'm trying to show you that, like, hey, here's a concept that you already know really well, but guess what? When we talk about moles, even though it seems like it's really confusing, it actually isn't at all. It's the same darn thing. All right. Are we cool with that? You know how to do that?
Yes.
Okay. What if I told you go out and buy 6 dozen eggs? How many eggs would you actually bring home? Well, in this case, we start off with 6 dozen and we multiply by a fraction to kind of convert it into a different kind of fraction, right? And which fraction would we multiply it by?
This one.
Why?
Because the dozens cancel.
1 does on the bottom and 12 eggs on top. So you have this cancels out with that. 6 times 12, what is that, 72? All right. Nothing crazy, right? This is like completely makes sense.
Yeah.
Right? All right. Now, you know what? I'm gonna do I'm gonna do the example problem. But before I do the example problem, I feel like maybe what I should do is tell you why the heck I'm showing you this. And my answer is this: we came up with this arbitrary number of 1 dozen means 12. Since you were a little kid, we've been telling you, hey, 1 dozen means 12. And it doesn't need to be 12 eggs. It could be 12 pandas. It could be 12 toothbrushes. It could be 12 teeth. It doesn't matter, as long as, you know, like 1 dozen means 12 something, right? And why is it 12? I don't really know. I don't know, but hey, 1 dozen means 12. That's all we've told you, right? And so you've got it in your head. You now know that this is the way it's packaged because, you know, it makes it easier to count things. If you have a large number of eggs, you don't actually count out 72 eggs. You just pick up 6 cartons and you're good. We're grouping them into things. But here's the problem is, what if I told you, hey, how many dozen grains of sand are there on the beach?
A lot.
Right. And so that's the point, right? A dozen might not be a good thing to use when you're talking about grains of sand on the beach, because it's so darn much that you could have like, oh, well, that's 150 billion dozen grains of sand. Well, yeah, dozen doesn't really help me with that. And when we're talking about really, really, really large numbers, or we're talking about counting really, 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 really small things, like how many individual atoms of plastic or whatever is inside of the cap of this pen. Now, this is not a very big pen. It's not a very big cap, but if you want to talk to me about individual atoms, there's going to be a whole bunch. And dozen doesn't count it, or wouldn't be able to cover it. It wouldn't make sense to group things like that. And so we need to come up with this number that is really, really big and standardize it and say, okay, from now on, that number is going to mean this very large group. And why do we need a very large group? Because we're counting very, very small things that exist in really large group, like the number of atoms inside this pen cap. If I even tell you like the number of atoms on top of a pin head, like a needle, on the very tip of the needle, how many atoms are there? Well, there's a lot. you know, hundreds and hundreds of millions of billions of atoms on top of there, and so we need a way to be able to quantify that, and so we came up with this thing called the mole. Now all the mole is it's a different dozen. It's a different grouping of atoms, or a different grouping size. And the reason why we didn't tell you about it before is because you didn't know about, you know, back when you were a kid, when you were learning dozen, we didn't say, oh yeah, hey, you know, hey, there's a dozen, and by the way, there's this new thing called a mole, which is 6.02 times 10 to the 23rd power of whatever, because you didn't maybe know exponents, because the grouping things in that size wasn't really, you know, helpful to you. But I guarantee you that if you know basically these two problems, which seemed like baby problems, my explanation of moles is going to be like, oh wait, is that it? All moles are is just grouping things in a different way? And the answer is yeah, absolutely. It's just grouping math. All right. So that's the trick, right? That's the whole point. But let's do example 7-1, and we'll start off with this. And I'm just going to stand up because I'm tired of sitting on this very creaky chair. All right. In fact, I'll switch places with you. I'm right-handed. I'll write on this side. Why don't you go over there? You gotta have a chair. Okay. All right, so check this out. We start off with 90 apples. And the problem asks, how many kilograms does that weigh? And it tells you that 1 dozen apples equals, was it 2 kilograms? I think the problem said, yeah, 2 kilograms. All right, you ready? So we start off with the thing we started off with. We know that we're going to convert apples to kilograms. So we're going to need to multiply it by some fraction in order to convert kind of the units on this one. So we have apples. What do you think? What's your thoughts?
I don't know, maybe like 1 kilogram for each apple?
No, it's 2 kilograms for 1 dozen apples.
Oh.
So if we have apples now, is there a way we can get from apples to dozens?
Yes.
How?
12 apples, 1 dozen.
Okay, good. 12 apples is 1 dozen. Cool?
Yeah.
Do we have another equal thing that helps us get from dozens to kilograms?
Yeah.
Yeah, cool. All right, so we set up another fraction.
2 kilograms is 1 dozen.
Okay, so wait, where do you want me to put the dozen? Do you want me to put it on top or bottom?
On the bottom, right?
Why?
Because they cancel out.
Yep. Apples cancel out with apples, dozen cancels out with dozens. And basically, the whole problem comes down to 90 divided by 2, or 12 times 2. Pull out your handy dandy calculator. I don't have a handy dandy calculator on me. That comes out to 15. Does that come out to 15? What's 90 divided by 12? 90 divided by 12 is 12 times 6 is 72. Another 12, that's 84. Okay, so it's 7.5. Multiply that by 2, you get 15. There we go. 15 kilograms. Is that hard?
No.
No, not really. Cool? So, let's talk about this guy Avogadro. There was this dude named Avogadro. I'm on page 173. He didn't actually calculate out Avogadro's number. Avogadro's number is, oh, here it is. Avogadro's number is this. Avogadro's number is this. I used to call it the avocado number because I love avocados. But 6.02, in fact, I think it's 6.0223 But anyway, 6.02 times 10 to the 23rd power of something is equal to 1 mole of something. This is Avogadro's number, 6.022 times 10 to the 23rd power. Ask me where 6.02 times 10 to the 23rd power came from.
Where did 6.2 to the 23rd?
I have no idea. The textbook doesn't say, I don't know. I mean, I guess I could ask the same question, where did 12 inches in a foot come from? I don't know. It just is. I know that it is something that it has been calculated. I have a feeling that what they did was they said, okay, hey, let's going to take a hydrogen and we'll take 1 gram of it, and then we'll count out how many atoms or particles of hydrogen there are in there, and that's how many that's how many particles there are in 1 mole. I don't know. It's just a number. It's a conversion factor. Why did they choose 12 when they chose a dozen?
Because 12.
I don't know, just because that's what it is. A dozen is 12. I don't know. All right. So basically, this is the new dozen in chemistry. And if I told you, okay, here, let's look at example number 7-2 on page 174. If I have 1.25 times 10 to the 23rd atoms, so I start off with 1.25 times 10 to the 23rd power of atoms of some element. What was this? It was an element of magnesium. How many moles is this? Okay. I just told you this fact, that 6.02 times 10 to the 23rd equals 1 mole.
So it's not even a mole.
Yeah, exactly. So this is not even a mole. So the answer is probably going to be some fraction of a number, right? Yeah, I agree. We need to convert this from atoms to moles. Just like we would need to convert this from apples to dozens. So how do you do that?
You just set up a conversion.
All right, we'll set up a conversion. Boom. Which one are we going to have on the bottom? Which one are we going to have on top?
Well, the moles are on top and atoms are on the bottom.
So 1 mole of magnesium is 6.02 times 10 to the 23rd power of atoms. Now, if I told you this was 6.02 times, or this was 1.25 times 10 to the 23rd particles, 1 mole is also 6.02 times 10 to the 23rd particles. I mean, it just, the something means you can put anything you want in there. It could be 6.02 times 10 to the 23rd little moles, like the actual animal of a mole or whatever. Yeah, I know, that was weird. But you could have like 6.02 times 10 to the 23rd, just whatever you want. But usually we would put the word particles or atoms or something really, really small because we're talking about a really, really large number. So, yeah. Okay, and you plug that into your calculator and you end up getting 2.08 times 10 to the negative 1, or 0.208 times 10 to the times 10 to the 0. There's no ones there. And then this is moles. That's it. That's how you do it. You seriously, that's how we do moles. It's just like converting dozens to, like eggs to dozens of something. It's doing the same thing. We're just using a different number.
Why do you spell the mole weird? Isn't it with only, isn't it E? Or it doesn't matter?
Oh, MOLS is, I think, abbreviation for moles, whereas MOLES, I think, is actually how it's spelled. Possibly. Or I could just be talking about the animal mole.
That's like a 1-letter difference.
Yeah, I know.
That's not an abbreviation.
I know. Why do you need to abbreviate the short word already? I don't know, because chemists and physicists and mathematicians, we're all lazy and we try to find as many shortcuts as we can. All right, check this out. How many atoms are in the number of, okay, this is a good problem. Okay, We're going to do problem number 7-3. 7-3. This is example problem 7-3. We have propane. The chemical formula for propane is C3H8. C3H8. Okay. We have 2.12 moles of C3H8. All right, I got a question. If I had 1 atom of propane, how many atoms am I dealing with here? Does that make sense? If I had 1 atom of propane, I would have 11 atoms in my hands.
Oh, yeah.
Because I would have 3 C's and I would have 8 H's. Okay? So we need to keep that fact in mind. So I think that the way we did it, in fact, I'm just going to use my notebook. And by the way, if you could hear singing or screaming in the background, that was my 7-year-old son. He's been watching Angry Birds 2, and I am going to not like the person who did the opera scene, because that's, yeah, that gets on your nerves. Okay, so here's what I'm going to say. You start off with moles of propane. Cool. Let's convert this into how many atoms of actual propane there are. So, how do we do that?
Wouldn't it just be 11? Or...
Oh, no. This is, I'm going to go from moles to atoms.
Oh, so you put the moles on the bottom.
Yeah, 1 mole on bottom. And then that crazy number. Do you remember what that number is?
6.1 02?
6.02 times 10 to the 23rd atoms up on top. Cool?
Yeah.
And then we know that for every atom of propane, there is 1 atom of propane, C3H8, is 11 atoms, MS, oh that's terrible, I'm sorry, ATOMS, of stuff. Does that make sense? And so you take a calculator and you literally just plug in 2.12 times 6.02 times 10 to the 23rd power times 11. As far as units goes, this is moles of propane, cancel out with moles of propane, atoms of propane, cancel out with atoms of propane, and then 11 atoms is how many atoms you're dealing with in the end, and you end up getting a number of 1.403. 1.4039 times 10 to the 25th power of atoms. Is plugging things into your calculator and dealing with exponents hard?
No, it's not hard.
Is dealing with dozens and converting like that stuff hard?
Nope, not hard.
Then moles aren't hard. Do you see what I mean? Like, it's not as bad as you think it is. If you think of it as just a new way of grouping things, then all of this stuff becomes like, oh, I get it. This is the way we convert it, and it's just a conversion factor. Leave it up to the physicists to choose the chapter that has the most math in it. Okay, let's see. What did they say here? Oh, they actually use the moles as an anomole. Where they, on page 176, where they talk about like, hey, if you had 1 mole of moles, I know they're being kind of cute, but they're saying like the little cute furry mole animal, actually they're quite ugly, weighs 150 grams, and if you had 6.02 times 10 to the 23rd of those kinds of animals, each weighing 150 grams, that would come out to 9.03 times 10 to the 22nd power of kilograms. That is more than the mass of the moon. That is 60 times the combined mass of the Earth's ocean. That's how much that would weigh. What we're saying is this number is astronomically big. It's bigger than you can ever imagine. I think I remember saying if we had marshmallows and we had 6.02 times 10 to the 23rd marshmallows. I think I remember when I taught chemistry like 5 to 10 years ago saying, oh yeah, that would cover all of America like 700 feet deep. You would have marshmallows stacked up all across America, stacked up 700 feet. It would drown everyone in marshmallows. That's how many, that's how big this number is.
I don't think it would drown anybody.
I think that we would drown in marshmallows. All right, well, maybe no one could complain, but I mean, just saying. Now, how do we use this in chemistry? Well, we're going to be using this, and there's this really cool trick that we use, and you've actually seen it before, and it's on our periodic tables. It's called the molar mass. And so what we would do is say that if we had the number of grams of something, and we wanted to figure out, like we had the number of grams of hydrogen peroxide. We measured it out and we said, we have 5 grams of hydrogen peroxide. How many moles or how many particles are in there or that kind of stuff? And we have this trick to do it, but in order to figure that out, we need to figure out this new conversion factor, and it's called the molar mass. So right now I'm talking about page like 178, 179, where we're talking about the molar mass. Let me do example 7-4. I keep losing my, oh there it is. Now I know. I'm sorry, I don't mean to embarrass you, but I think it's helpful for you to kind of answer these questions and interact, and just let's talk about it, man. I'm not trying to, I'm trying to help out in a crazy situation, you know what I mean? 7-4. So what we're going to do is we have hydrogen peroxide, H2O2. And what we want to do is we want to figure out, if I have 1 mole of this, how many grams does that weigh? And basically figure out a conversion factor for that. So like 1 gram of H2O2, or we'll do it this way, is 1 mole. 1 mole of H2O2 is equal to how many grams of H2O2? Because after that, we'll start being able to use this in a conversion where we'll be able to make a cool fraction from this, math fact.